This physics class is studying the principle of acceleration. The activity begins with a brief review of similar experiments and graphing techniques needed for the day's lesson.
If I get a line shaped in that general direction, what does that mean? Jeff?
It's like directly. One is directly proportional to the other.
Directly proportional. What happens if we see a shape that doesn't look like that, does something like that? Lori?
Oh God, I really don't know.
It's okay. James?
Well, it's not directly proportional.
It's not direct, it's indirectly proportional. Lori, you did know after all.
The learning activity that we did today is related to Newton's laws. The kids have used the computers to do velocities and time, so they're kind of used to doing that, and they're starting to learn how to graph variables and how the variables relate to equations. And today we're looking at the mass and acceleration, and we are trying to get the relationships between force, mass, and acceleration. And the kids are going to struggle. They struggled a little bit with determining how to do it. We start the year with a ticker tape, the old-fashioned ... to get the velocity. Then we move to the computers, and now what they don't know, and they almost discovered, is they have to use 2 photo gates to get acceleration, and we'll put that on them the next time. We let them struggle a little bit today. They didn't get very good acceleration readings because what they know how to do is velocity. So we didn't get the second gate out and show them how to do everything yet. We kind of pieced that together one at a time. So the technology works as a tool to solve problems as we go along.
The teacher describes the day's lesson to the class. Students will create their own experiments to calculate acceleration.
Go look at the materials if you want to that I've laid out. Okay, those are the things that I want you to use. You know about photo gates, you know how to use them. You've got your computer interface, and I just set cars out. There's masses around. If you've got a better plan, do it. But look at those materials, make your plan. Now you're going to have 2 things that we're going to be looking for. First thing is a plan. I want to know what you're doing. What are you going to do? What's the plan? Second thing is I need to see what your data is going to look like. How are you recording your data? What are you recording and how are you recording it? And then finally, what are you going to plot or what are you going to graph for me so that we can find a relationship between these 3 variables? Where are those variables? 2. You need to figure out where they're at.
Students break into small groups to design their experiments. Their plans must be approved by the teacher before experimentation can begin.
Oh, we need a card. Set that up. Then if we just run the cart down the ramp, and then have it go through the photo gate, it should tell what the acceleration is. I have to get some right weights.
I'm needing a note card.
Hey, Mr. Munson, do we have a note card?
Do we have a note card?
No card.
Once their plans have been approved, students perform their experiments and record the data they gather. Several trials are needed to evaluate their data and refine their original plan.
Measure in centimeters.
12 centimeters.
No,
But
we're doing
measure it that way.
Well,
Get back
this
together. We
is
got to make sure everybody shares that.
7.5 centimeters.
Okay.
How is that, what unit is that in?
0.075.
Read it.
See that in
Okay. Yeah. That'd be 7.5 centimeters. Because that's in
Is
meters.
it in meters? Okay, so that's good then?
Yeah. You can close it.
Please don't let it go.
You ready?
Ready? So then 0.069 and 1.07.
Okay.
Want me to do 200 again?
Yeah.
0.0695.
37.
Okay, there's 150 on the car and then 50 on the thing.
Okay, you just take it, push it back, Jeff.
You put 150 on the car?
150 on the car. Because I didn't want to mess with hanging them off the ends of the waist because we kind of got a lot of them.
Oh. Oh, yes.
0.15.
Oh, that's a definite.
Let's try it the other way. Let's put the 50 on the car.
0.490.
I don't know how that's what.
1.4989.
That's right.
But I'll try it. Yeah, that's switch it around.
The teacher gives assistance to the students by lending an extra hand or giving suggestions that guide their research.
It's not even on the string. It's gonna drop.
Okay, awesome.
Make sure it's on the board.
Okay, there we go.
Are you ready?
Oh, I'm ready.
Okay.
Oh my god.
Worked.
Let's say that you have 100 out here at the end of the string. Here's a good question. If you had 100 out here and you had your car, and then you put 50 out here and put 50 there, would there be a difference?
Yeah.
There would be.
I would weigh more.
I don't know.
Okay, ready?
Maybe you should try that too. Just at the end, try that. Try to keep the total mass of the system the same, but move it around. Move some to the car, move some to the end.
The activity ends with students reviewing and graphing their data. The teacher works with them to point out factors they may not have noticed in order to calculate acceleration.
Jeff, did you do one where you kept the system the same at the end?
Yeah.
Did they change your numbers much?
When we had 150 in the car and 50 in the string, it was 0.15. When we had 150 in the string and 50 in the car, it was...
Okay. If you look at, this is your weight. Your force is going up. What's happening to your velocity, to your acceleration?
going up.
Going up. So what kind of relationship are we looking at?
Direct.
A direct. So if you look at force and acceleration, we're direct. So general shape, something like that. Now, look at your last numbers that we did. When we took the mass, and here we increased the mass of the car, and what happened to our acceleration?
Went down.
Went down, keeping the force. If, in other words, if I loaded a bunch of weight on my, if I kept this the same
Yeah, okay.
and loaded a bunch of weight here, what happened?
It did go down.
Go down. So what's the relationship mass and acceleration-wise?
Inverse.
Inverse. The mass is the only thing that the question, I had Jeff do this. This is the force. No, there's no argument there. Remember, how much mass are we moving here? Just the car?
Yeah.
Are we also moving this? That too. So in a situation like this, when we look at the mass, we should really think of mass, and that's a mistake that some of us made, as a combination of them both.